Researchers from the Galician Institute of High Energy Physics, or IGFAE, which is a joint center of the USC and the Junta de Galicia, like thousands of others around the world, work at CERN, the European Organization for Nuclear Research. Located in Geneva, CERN is the world's leading particle physics laboratory. Therein, researchers study particle physics using various highly complex experiments, the most important of which is the Large Hadron Collider, or LHC. To understand what we do, let's first answer a few questions. Matter can be broken down into smaller pieces until we get to what we call molecules. Molecules, in turn, are made up of atoms, and atoms are divided into two parts: a shell, which is made up of electrons, which are indivisible particles of negative charge that orbit around the atomic nucleus, which, despite being tiny, concentrates almost all the mass of the atom. The nucleus itself is composed of positively charged particles called protons and uncharged particles, the neutrons. However, the protons and neutrons that make up the nuclei can also be subdivided further into other, smaller elements known as the U quarks and D quarks. It is important to remember that almost all the mass of an atom is concentrated in the nuclei, even though they are tiny. In fact, the nuclei that make up the universe in which we evolved differ from each other depending on the mass they contain and the number of particles that make them up. In order to better understand the function of the entire universe that surrounds us, particle physicists have spent their time understanding how the fundamental components of matter are formed, structured, and related for just over a century now.
The Large Hadron Collider, or LHC, is an accelerator consisting of a 27-kilometer ring located 100 meters underground, where protons are made to collide at almost the speed of light. These collisions produce secondary particles that live for a very short length of time and are observed by the LHC detectors, which can be thought as of huge cameras. Today's detectors, like LHC-b, reconstruct most of these particles, and they provide us with a wealth of information on what happened after each collision. With this data, the fundamental structure of matter can be determined. However, there's a hypothetical class of new particles which live longer than most of these produced in collisions, and which escape our existing detectors. This is either because the detector does not cover all possible angles, or because some particles live too long before decaying, thereby escaping detection. This second scenario is especially difficult to avoid, even with the largest detectors that currently exist at the LHC. For this reason, we want to take advantage of the existing space around current instruments to construct new ones, further away from the collision point, to track these new types of long-lived particles. Here at IGFAE, we are involved in the development of codex-b, a detector that will be located in the same cavern as LHC-b, behind a concrete wall that will prevent us from detecting background particles that could confound the search for these long-lived particles. Discovering a new long-lived particle would be revolutionary and could challenge many of our conceptions in physics, raising profound questions on the nature of the smallest building blocks of matter to the origin and composition of our universe.